In this video, we're going to investigate the formula for the area of a surface S above the region D of the UV plane and finding the area of that parametric surface, okay? And what we're going to do, we're going to wind up adding tiny tangent planes together until we make up the whole surface, because we'll let the we could even say let the norm of the partition approach 0, the partition being the size of the tangent plane. So this, maybe we could say the diagonal of the pieces of the tangent plane approaching 0. The tangent planes that we broke it up into. There, that's better. So this assumes the tangent plane to a surface near a point is almost the same as the surface near the point, which is a good assumption. So if we cut D into tiny rectangles, wee little rectangles, then the surface above each rectangle is approximately the same as the tangent plane above the rectangle, right? So that's what our hope is, and that will be some sort of a parallelogram, and we're going to add up all those parallelograms as we let the size of the partition approach tiny. Anyway, the area of the parallelogram is formed by finding the length of the cross product of the two vectors. Remember, that's how you find the area of a parallelogram. One of the ways you can find the length of the cross product of two vectors that span it, okay? So, namely, delta u times r of u, or that's dot r of u, my fault, and delta v dot r of v, where delta u and delta v are small intervals in the UV plane. Okay. The length of the cross product is this, and that's the length of r. Well, we'll call that the partial of r with respect to u cross the partial of r with respect to v, times del u times del v, and the sum of all the parallelograms approximates the surface as these pieces approach 0. Those are the pieces that we chopped up the u and v axis into tiny bits like that. Okay, so the area of parametric surface, if S is a smooth surface defined by this vector valued function, defined over region D in the UV plane, if each point on S corresponds to exactly one point in the domain, well, unlike example 1, remember why that wasn't good? There were places where it was, well, let's put it this way, it would not be considered a one-to-one function, right? I think the one that looked like a waste basket wouldn't work very well either, but okay, here we go. The surface area is double integral del S over the surface S, which is the cross product of the partial derivatives of the vector value function with respect to u and v over our rectangular domain D, or might not necessarily be rectangular, but our domain D, which is some subset of the UV plane, times dA, and you kind of know what the dA is going to be. So we got our u as this set of partial derivatives times the I, J, and K, and our R, V, same. You know how to get those anyway. So for any surface defined like we did in Unit 4, that the formulas are the same, since we can write the vector value function for the surface as this, right? X here, Y here, Z there. So it's the same sort of thing we did there. And R of X would be I plus partial with respect to X of F of X, Y times K, and partial with respect to Y would be J plus partial of F X, Y with respect to Y times K, forcing this product to be, cross product to be negative Fx of xy times I minus Fy of xy times j plus 1 times k. And therefore, okay, our Rx cross Ry is square root of 1 plus Fx xy squared plus Fy xy squared. and look at the formula from Unit 5, Lesson 5 that talked about surface area to compare your answer. So sketch and find the surface of the torus given by r of uv equals 1 plus cosine u times cosine vi plus 1 plus cosine u times sine of ej plus sine of u times k, where d is given by u goes from 0 to 2 pi, and so does v. So it's a rectangular region, right? So here's our f of u given in parametric form. Here it is, here in vector valued form, right? I'll try to highlight the whole thing. There it is in vector valued form. Here it is in parametric form. And here's our picture, but that's not our surface area, right? That's the picture. It's called a torus. You could say it looks like a green donut, right? That's one that's been out in the sun too long, huh? So let's see if we can find the surface area. All right, well, RU is the partial derivative of this with respect to u, and that would be, let me see, partial of 1 is 0. Partial of cosine of u is negative sine of u, but don't forget this would be a constant, so it's negative sine of u times cosine of v. See? Times I. Okay. Didn't do the all I did was the partial with respect of u of the I part. Now let's do the partial with respect to u of the j part. Hey, same thing. Negative sine of u times sine of v this time. See? Negative sine of u times sine of v. Okay, and let's go back and get the partial of this with respect to u. Of course, the partial, it's just the derivative of sine is cosine, so we got cosine of u. Okay, now we got to do the same thing, only not with u, but with v. Okay. Look at our, oh, I have a mistake. This is supposed to be a 3, my fault. There, it's fixed. Okay, now, partial of this with respect to v, this whole 1 plus cosine of u is a constant, and the derivative of cosine is negative sine, so we should get negative. Now, daggone. Well, it didn't show up that that was supposed to be a v also. Now, hang on there. You know, I must have started one problem and written another. Sorry about that. But, okay, I think we still want everything's still the same. And when we take the derivative of this one with respect to u, we still get the same thing. The derivative of this is 0, so the derivative of 3 times that's still 0. We do get the derivative of this, which is negative sine of u times cosine of v, so that winds up the same. But now we're going to get something that's going to wind up a little different, because when we take the derivative with respect to v of this part, you know, then the 3 plus cosine u is a constant, and the derivative of cosine is negative sine, so we're going to get negative. There's the sine, there's the negative part out here. So we're going to get this constant, 3 plus cosine u, times negative sine of e, times I, okay? I'm going to just say similarly, take the derivative of this with respect to v. We get cosine here then, and this is still a constant, so 3 plus cosine of u times the derivative of sine of e is cosine of e. And then finally the last part, the derivative of sine of u, well, this is with respect to v, so that's this derivative of constant, which is 0. So these are the two vectors I want to find the cross product of. So here is that cross product, okay? This cross product, a little wild and crazy, but I think you can see, and you can do this with determinants. This is a factor of, the entire row 3. Of course, 0 doesn't matter. We can factor it out and make it a constant. There it is, factored out, and it's a constant. A nice constant, factored out constant. So our cross product is going to be this, the constant, and then times I times this minor, that's this times this, which is 0, minus this times this, which is minus cosine u cosine v. So we got I, where is that? I times cosine u cosine v, don't forget this is a factored out constant. Okay, and then minus j times its minor, which would be this times this, which is 0, minus this times this, and that's going to give us minus, remember, because we had a negative in front of the j. So minus, it's like 3 negatives, believe it or not. So minus sine of v cosine of u, and then plus k times this one, which, oh, that's going to be the tricky one. That's cosine squared times negative sine, and this is, that's cosine squared, I should say, of v times negative sine of u. And this one, look there, is sine squared of v times negative sine of u, so it's just going to be sine of u, but I'm wondering if I made a SIGN mistake. K times this is cosine squared, and that's negative sine, factors out. And this times this is positive sine squared, but that's actually got 3 negatives in it, so that's negative sine of u factors out times 1. So I believe I have a sign mistake, and this should be a negative. Oh, rats. I'll fix it. It'll just take me a while. Negative, does that do it? No, not quite. It almost did. How about if I put it here, the cursor, and then put a minus? Ah, beautiful, just what I wanted. So, all that sweat to get the sine of the sine, you met the sign of the sine right, all that sweat, and I'm just going to square it anyway, but bear with me. Square this mess, get this mess. Square this mess, get this mess. Square this mess, get this mess. All right, we got our messes taken care of. Now, nice thing here is I think something factors out and cancels. See, we got cosine squared u here and here. So factor that out of these two terms, we get cosine squared of u times cosine squared of v plus sine squared of v, which is just 1. And then that cosine squared of u and this sine squared of u come out to be another 1. So after all that, the length of that vector is, hallelujah, 3 plus cosine of u. All right, remember how I wanted that? The length of this vector, right? The length of this vector, right? Okay, that's so long ago, I wonder if you'd still remember. All right, so that becomes our integrand. U and v both going from 0 to 2 pi. So, well, it's pretty easy. This is 3u plus sine of u. And sine of u at 0 and 2 pi is 0 in each case. So we get 3u, u going from 0 to 2 pi, so we wind up with 6 pi. This is first 6 pi. All this is 6 pi. And then we want to evaluate that with respect to v. And 6 pi going from 0 to 2 pi, so this is 6 pi v. V goes from 0 to 2 pi, so it's 6 pi times 2 pi, which is 12 pi squared, which is the surface area of our donut.